Dan McIntosh from UMKC, chairing the last session. So I am happy and pleased to introduce the first speaker, Kameswara Mantha, who's going to talk about his part of his PhD thesis project.
Awesome. Can you hear me okay?
Yep. Yes.
Awesome. Like Dan McIntosh just introduced me, I'm Kameswara Mantha. I'm a graduate student at UMKC. In collaboration with the members of the UMKC Galaxy Evolution Group and also UMKC Galaxy Residual Analysis Group. And also I would love to acknowledge my collaborators here for this work, which talks about galaxy mergers and the observability timescales of the closed pairs that galaxies exhibit using something called semi-analytic models. So before I jump in, I want to talk about what is galaxy merging. So I know you're already tired listening about galaxy mergers by now, but galaxy mergers are when two galaxies sort of gravitationally interact with each other in close physical proximity and then coalesce to form one massive system at the end of it. So motivated by many simulation-based studies and also empirical studies, here's a picture that has been very famous, which is the galaxy merger, galaxy evolution connection, where galaxy mergers are thought to sort of transform galaxies in terms of their colors and also their morphological features. Where you see two spiral galaxies, they collide with each other, and then at the end of it, they form into a round-looking thing, which is like an elliptical galaxy. They're transforming the galaxy. My primary research interest is to understand the role of galaxy mergers in this sort of grand context of galaxy evolution itself. However, I want to emphasize that this still is an open question, quantifying the importance of galaxy mergers in galaxy evolution. And two of the important things to do this is to first identify galaxy mergers properly. The second thing is to quantify the galaxy merger rates, the rate at which massive galaxies experience galaxy mergers over cosmic time. And understanding the evolution of this quantity is key. This is something that I'm focusing on for my thesis. So there are two empirical techniques that are frequently used, motivated by simulations. The first one is called the closed pair method, and the second one is using tidal features. Closed pairs are where you select galaxies that are in close physical proximity, i.e. in projected distance and also in redshift space, to select plausible merging candidates. The other way is to select galaxies that host hallmark tidal signatures caused by tidal forces during the merging process itself. So using these two different ways, you can select galaxy mergers. So I know I got peer pressured into thinking that I will talk about this today. I know a lot of people said yesterday I'm going to talk about this, but actually I'm focusing on the first part. But to complete the sentence, I have developed a new method that would extract these hallmark signatures. If you're really interested in doing so, please come talk to me after the talk, and I'm happy to talk to you.
And see the paper.
Yes, and I'll see the paper. So let's talk about closed pair method. So basically, just to reiterate, so you select, this is an example image of a galaxy merger happening at redshift of 1 from the Candles survey. The image is in H-band, and the primary concept behind this is to select galaxies in close physical proximity, the projected distance, and then at a specific redshift difference. And also, the primary galaxy and the secondary mass of the galaxy should be comparable to each other, such that we are selecting major mergers. This is what we call major merging. And one key equation that I'll come back again and again during this talk is this simple equation. Merger rate of galaxies is quantified by the closed pair fraction, the fraction of galaxies hosting closed pairs, divided by an observability time. Simply, this observability times means that if you had the ability to just like watch a merger happen in real time, what time window does it present itself as a closed pair? That's called the observability timescale. And this, as you will see, is going to play a really important role in quantifying the merger rates robustly. Now, what do we expect from numerical simulations? So here's a paper from Vicente Rodriguez Gomez et al. On the y-axis, you have galaxy merger rate as a function of redshift. And you see from the illustrative simulation, they have followed the galaxies in the simulation and computed the merger rate as a function of time, and they find that it should rise steeply, i.e. they are more frequent at high redshift, they're not as so frequent at lower redshifts. This is what we should expect. However, if you look at the collection of recent studies that quantify the closed pair fractions, the fraction of galaxies hosting closed pairs on the y-axis here on redshift, you see a lot of points here. But let me just sort of break it down conceptually on the right-hand side plot in here. If you were to observe all these points at starting from redshift of 1 to redshift of 3, you would see that it's sort of flat in trends. So the issue here is that the observability timescale that I introduced to you earlier is often used or assumed to be a constant number. What do I mean by a constant? They usually assume it to be not evolving with redshift, meaning that it's a constant fixed factor as a function of redshift. And naturally, if this is the trend that we are seeing observationally, which is flat, if you were to divide this with a simple number, the pair fraction is going to sort of start to disagree with the merger rate that you expect from the numerical simulation. So you can see that at high redshifts, the predictions sort of deviate from our observations. So observation starts to disagree. And this is a problem. And a study done by Greg Snyder in 2017, what they did is in the same illustrious simulation, they went in and they created this mock universe using, by observing the simulation as if it was real observations, and then counted up closed pairs in them. And then they found, again, it to be flat. Now, let me put into perspective of what this actually means. If you were to assume Greg Snyder's points here as, these blue stars here, and the gray line is the merger rate from the same simulation, they concluded that in order for the closed pair counts to actually make sense in the context of the actual merger rate, the observability timescale needs to shrink as a function of redshift, meaning that it should get shorter and shorter at high redshifts. That means that the fraction of time you'll catch a merger in a closed pair state is shorter at high redshift. That's what this means. But they did this only with one mock catalog, and they concluded that the power of the redshift evolution is -2. But it is hard to say, I want to follow this up. This is what my goal is. And what I want to do is I want to use a large suite of semi-analytic model-based mock light cones generated by 4 different leading semi-analytic models by the universe machine, which was recently released. And then these 3 are the sort of the established candles semi-analytic models that people have discussed for a long time. Just to elaborate what a semi-analytic model is, a semi-analytic model uses the output of an n-body simulation, usually something called as the merger history of halos, and then literally just paints galaxies on top of it using some sort of analytical prescriptions. And then this plus this gives you galaxies. That's how they create these mock universes. These are not exactly simulations, but these are semi-analytic approximations of simulations. I want to use these mock universes to understand to extend what Greg did in his 2017 study. So the first step I did is to quantify the pair fraction, the fraction of galaxies hosting closed pairs as a function of redshift, the same plot. Here's my closed pair selection. If anyone's interested, they can look at this. But immediately, I want you to take away that the closed pair fraction in the universe machine, which is one of the latest semi-analytic model-based mock, I find the same flat trend. And to emphasize the discrepancy, I'm overlaying the illustrious-based merger rates on top. And you can see that there should be a timescale evolution. It is sort of evident here. But I also applied the same on all 4 semi-analytic-based mocks. And then here's the puzzling thing that I'm still scratching my head. So based on which SAM I look, there's different trends in which the pair fraction evolves. The universe machine, there's no evolution with redshift. There's a weak evolution in one of the mocks, and also in the SAGE mocks, there's sort of weak evolution, and then there's a strong evolution in one of the SAMs. So nevertheless, I just want to infer timescales for all the semi-analytic models, and then give full disclosure, and I want to say, if you believe this model, this is what the timescale needs to evolve like. That's what I'm going to do in the future. But just what I'm going to do just for one example case is take the pair fractions and compare them to the intrinsic merger rates from the simulations, and then infer a timescale, literally inverting the relationship. Merger rates, the pair fraction divided by the merger rate gives us an observability time. And what I found based on simple calculations is that the observability timescale from my calculation should evolve like this. And for node, this is sort of less steep evolution than what Greg Snyder predicted. So this is, I just want to caution that this is still preliminary analysis. I'm going to extend this in a more rigorous sense. There are some caveats I'd like to discuss if anyone has any questions. But this is the current state of my work at the moment. Cool. And finally, just some upcoming work. So the observability timescale need not only evolve with Redshift. The important point is that the observability time will depend on the closed pair selection as a whole. So the closed pair selection will have many terms: Redshift, the primary galaxy mass that you select, the mass ratio, the projected distance, and also the velocity separation. So I want to quantify this timescale by simultaneously computing the closed pair fractions and comparing it to the real answer, and then infer all of these parameters: beta, gamma, chi, and eta. I want to build a scaling relationship. That's what I want to do. This is an upcoming extension of what I'm doing currently, and this will be discussed in the paper that I write. So finally, just to take away 3 important points from my talk, if you don't remember any of it. So 3 points is that there's a strong need to understand the closed pair observability timescale evolution properly in order to fully constrain the merger rate of the universe. And I'm using the semi-analytic models to do this, and I'm interested in galaxy mergers and tidal features. So if you're wanting to talk to me about this, I apologize again for not talking about this here. So if you can come talk to me or read these 2 papers on archive to know more. Thank you.
We have a little more than 3 minutes for questions. Students first. Sorry. I'm hoping for students first to pick up the trend from last time. There's a student.
So you had 4 different semi-analytic models. You said that like 2 of them were weakly evolving, one of them was strongly evolving. But how inconsistent with those? Like, how inconsistent are those evolutions with no evolution? Because certainly one of them looks pretty flat.
It's true. That's a good point. I did not fit a power law to them, and I did not test for the deviation from being, or consistency with being flat. That's something that I should do, and I have not done that. I will do that. And maybe they might be flat. But this shows evolution just by eye. But you might be right that these are actually consistent with being flat. I should test that.
So I had a clarification about the observing timescale. When you were talking about observing timescale, are you talking about the intrinsic timescale of a merger, or you're talking about like surface brightness dimming effects, like how much we can observe?
So,
because at high redshift, it's harder to find mergers, observe them.
Yes. So just to clarify, I'm not talking about the intrinsic timescales.
Okay.
So when you're observing closed pairs, we cannot divide them with the intrinsic timescale that they take to merge. That does not give us the merger rate.
Right.
Instead, what we have to divide it with is the observability time, which is the window during which they'll present themselves as closed pairs. So it's for example, if you were to observe a simulation and then count up what fraction of the time do they satisfy the closed pair selection criteria we are using specifically, that's the time we have to divide it with.
And so with your close pairs, though, remind me, are they all pretty close in mass? So could this be telling us about an increased importance in minor merging as we go up in time? So they're all pretty close in stellar mass.
Major merger.
So they are major mergers. So the mass ratio is less than 4:1.
Okay.
So
And the sample's complete.
yes, and so I'm struggling to understand how you're connecting from that aspect to
No, I was
the
just
minor
wondering
mergers.
if there is something else that could make up other mergers that could make up the
So
difference.
I exactly know what you mean. So you're suggesting that the mass ratio aspect of the selection might be missing mergers at high redshifts, and that's why you're seeing this sort of flat trend. That is a possibility, but so I know Allison Mann and collaborators, they have proposed for using the total baryonic mass as a proxy, as a better proxy for measuring major merging than just the stellar mass ratio, because the gas fractions at high redshift are high. So it might end up being like, if you were to plot the total baryonic mass ratio versus the stellar mass ratio, you would have these galaxies that are minor according to the stellar mass scattered into being major. And that is a possibility. I don't know if anyone has tested it. I know it's still in the process of doing that. So I might do that with my selection and see what happens. But that's a great point.
Okay, that's all the time we have. Let's thank Kameswara again.